All right, let's jump straight into this explainer on rig electrical drive topologies. Today, we're tackling the absolute biggest design question you face as an engineer when you need to power multiple motors on a massive offshore structure. We're looking at the true mechanical heart of these operations and the vital decisions that dictate exactly how that heart beats. Picture a rig with 3 heavy-duty motors. Maybe it's a drawworks, a top drive, and a mud pump. Do you give each one of these massive mechanical beasts its own complete, isolated power conversion system? Or do you build one highly efficient shared system and simply split the power 3 ways? That single question defines everything we're going to cover. So here's our mental map for this explainer. First, the core question. Second, single drive defined. Third, multi-drive defined. Then, the multi-drive advantage, followed by the redundancy catch, and finally, the final choice. Section 1. The core question. This brilliantly illustrates our 2 completely different paths side by side. Over on the left, we've got the isolated, independent drive per motor setup, and on the right, you can see that centralized, shared DC bus architecture. Let's see how the power actually flows in both of these. Section 2. Single drive defined.
Okay, so here's the deal with single drive topology. Absolutely nothing is shared. Each converter is fully independent. It has its own diode rectifier, its own inverter unit, and its own dedicated supply breaker feeding it directly from the switchboard. If one unit fails out there on the water, it fails entirely alone without taking down the rest of your operation.
Now you can really see the sheer amount of hardware it takes to actually maintain that isolation. Every single motor needs its own independent feeder breaker, drawing from that 690-volt switchgear up at the top. And because they're flying solo, each drive demands its own individual harmonic filter to keep the grid clean, plus a dedicated braking resistor. It is incredibly redundant, sure, but man, that independence takes up a whole lot of real estate.
Section 3. Multi-drive defined.
Multi-drive completely flips the script. Instead of running one heavy supply line per motor, a multi-drive system elegantly uses just one common supply feeder and one common diode rectifier for a whole group of inverters. So if you've got a 4-motor group, instead of 4 rectifiers and 4 breakers, you just need one of each. They all just tap off a shared pool of direct current energy on that shared DC bus.
And just look at how much cleaner this layout is. Up at the switchgear, you only have 2 main feeders, instead of that massive row we just saw in the single drive. You don't have those mandatory individual harmonic filters cluttering up your space, and all the internal cabling is beautifully centralized right around that shared DC bus.
Section 4. The multi-drive advantage.
Think about this. When a massive drawworks motor lowers a heavy load, it basically turns into a generator, right? It's creating immense amounts of energy. Now, in a fully isolated system, you have to dump all that energy as raw heat into these big braking resistors. But in a shared multi-drive system, where does that power actually go? This is where the engineering gets almost magical. Because these inverters share that essential DC bus, energy from one motor that's braking can flow directly and instantly into another motor on the same bus that happens to be accelerating. It moves right through the bus itself, no extra hardware needed. It's like a perfectly choreographed seesaw of electricity, completely bypassing those massive, hot resistor banks entirely.
Let's do a quick mental check. Based on what we've covered about how power is drawn, which system strictly requires a bulky harmonic filter on every single individual drive just to keep the rig's power grid clean?
Right, it's the single drive. Since those units draw distorted current completely independently straight from the switchboard, you have to filter every single one of them. Multi-drives, though, they brilliantly centralize and filter that distortion just once at the common rectifier. That saves a massive amount of component cost and actual physical steel on the deck.
Section 5. The redundancy catch.
So multi-drive sounds amazing, right? But it all comes down to sharing risk. In a multi-drive, sharing that DC bus is incredible for efficiency. But if you lose that one common rectifier, every single connected motor downstream dies simultaneously. It is a single point of failure. On the flip side, a single drive system guarantees that one catastrophic failure will never cascade. The others just keep on running.
Let's apply this to a real-world scenario. Say you are designing a critical drawworks safety system where losing all of your motors at once isn't just a minor inconvenience, it is an absolute unacceptable disaster. Which architecture must you specify?
You specify single drive every single time. When operations demand that a fault absolutely cannot spread, full electrical isolation is the only mathematical way to guarantee true redundancy. You are happily trading the footprint and the weight savings for the ultimate peace of mind that one blown component won't drop the entire load.
Section 6, the final choice.
As the engineer making the final call, you have to meticulously evaluate a whole matrix of parameters well before the first piece of steel is ever cut. We're talking physical dimensions, total system weight, the regenerative braking capacity you need, harmonic distortion limits, all the way down to shipyard delivery times.
It really all boils down to your vessel's specific constraints. How congested are those cable trays going to be? How much motor-to-motor braking efficiency can you realistically leverage based on your duty cycles? And, crucially, what is the absolute worst-case scenario if you tolerate a centralized point of failure on this specific system?
You are constantly tipping the scales between two extremes here. On one side, you have the space and cost savings, the immense physical efficiency of sharing power via the multi-drive. On the other side, you've got redundancy and harmonics, the rock-solid bulletproof safety of complete electrical isolation provided by the single drive.
Now that you understand exactly how the shared DC bus is the mechanical linchpin for both massive efficiency gains and the terrifying potential of a total system blackout, the ball is in your court. The next time you're staring down a multi-million-dollar electrical layout, how will you tip the scales? Which path will you choose to power your next project? Thanks for joining me on this explainer, and we'll see you next time.